Okay. Can everyone see this fine? Or should I zoom in a little more? I'm actually not sure how to zoom in on my laptop. Is this fine? Or should I make it bigger? Okay, I'm just going to assume this is big enough. All right. So we're going to be talking about a subject that I just call Andy the Unicorn. Oh, what the heck am I doing? All right, so today's talk is going to be about Andy the Unicorn. And the reason I give this description is because, well, it's this whole new class of problems. It's a whole new type of problems, probability problems that I am pretty sure that none of you have seen before. All right. So the idea is, when do we want to throw away information? And the idea is, your ordinary probability problems are quite simple. You just find the number of desired outcomes and divide it by the total number of total outcomes. All right, so if, for instance, you'll look at this, your ordinary probability problems, for instance, let's say you have John rolls a pair of dice. All right, so what's the probability that the sum of the faces that he gets is 11? Right, so this one is really simple. The only possible probabilities are, 5, 6, and 6, 5. Yeah. Right. And then these are two possibilities. And these are two possibilities for desirable outcomes. Now, when it comes to total outcomes, we have to make sure that the way we count it is consistent. Now, you guys might be thinking this is completely obvious, we know how to do this problem, but it will come into play very soon. So the idea is, you have 6 times 6, because the first die can roll any of 6. The second die can roll any of 6. They're independent. So this is 2/36 or 1/18. However, what if we can't count the total? What if we don't know how to count the total? What if we don't know how to count the number of desired outcomes? And here is where Andy the Unicorn the idea really starts to come into play. You're not looking for the total number of outcomes. You don't want to count the total number of outcomes. You want to look in a small area. And here is what I mean. All right. Let me copy the problem statement real quick. All right. So here we go. Okay, stop there. So here is the zinger. Here is just the problem. Andy the Unicorn is on a number line from 1 to 2019. He starts on 1. And each step, he randomly and uniformly picks an integer greater than the integer he is currently on and goes to it. And he stops when he reaches 2019. So what's the probability he ever reaches 1984? Sorry. Anyway. So let's just show what this problem means. So let's just say He's at 1, right? So there are 2018 numbers between 2 and 2019, and he lands on any of them with equal probability. Okay, let's just say he goes to 1379. All right. Then out of the remaining numbers between 1380 and 2019, you know, and there are 640 of them, he lands on any of these numbers in front of him with equal probability, and he keeps jumping forward. And the reason he might not ever reach 1984 is because he could skip over it. All right. So immediately, we are starting to see an issue. Your first instinct, and my first instinct when I wrote the problem, was to think, okay, is there a way I can count, you know, the total number of ways he can land on 1984? So, and of course, also the total number of ways he can get to 2019 at all. And, you know, you might think, okay, he can go from 1 to 2 to 3 to 4. And then like to 1984, and he just visits every number. That's one way. Another way is he just jumps straight to 1984, and then he jumps to 2019. Now, the issue with this idea is that the probabilities of these two events occurring is not the same. This relies on a lot of things happening, a lot of, you know, proverbial dice roll going your way. So the probability is low in comparison to this probability, because this only requires two events to go your way. Now, I'm not going to calculate the exact probabilities, but it's low. Oh, someone already figured it out. Congratulations. Or unless you've seen it before. Anyway. So the idea is you don't know how to count, because these two events don't happen with the same probability. If we look back at our previous slide, it was completely contingent. You know, up here, it was completely contingent on the two dice roll being the exact same. Like, you know, every possible outcome has the same probability. That is a fundamental idea in combinatorics. You know, that's how we solve probability problems. Otherwise, we have nothing. And here, we have nothing. We can't solve the problem because we're taking an old concept of trying to get, you know, total desired over total, and that doesn't work because not each thing has the same probability. Now, what we're going to do is look at this problem for a little bit. But I'll give you guys a little bit of time to look at this problem, but I'm going to show you guys a related problem very soon, and that is going to be the hint. And we are going to do this related problem, and we're going to you know, take it step by step. We're going to explain the motivation of the related problem, and then finally we are going to jump, you know, to the problem itself, and we're going to look at it and we're going to explain it. And the solution is surprisingly beautiful. And I think, honestly, this is one of the nicest problems I've seen. All right. All right. So without further ado, we're going to take a look at the similar problem. And I'm going to clear the screen. So 64 balls labeled with the integers 1 from 64 are placed in a bag. Balls are removed from, I'm not good at spelling, from the bag without replacement one by one until a ball with an odd number is removed. So what's the probability that you remove 42 at all? Now, you're thinking, but Dennis, we've got the same issue here because, if you try it for a bit, you'll realize that not each thing has the same, not each outcome has the same probability. And, you could theoretically sum together all the probabilities, but that's not a very, fun approach. It doesn't seem very viable. And when you've just got a few minutes, you can't do that sort of calculation. It's not very consistent. And here's what I mean by the probabilities are equal. Let's say you pull 2, 4, 6, 8, whatever, 42. Then you pull an odd number. Now, that is quite, unlikely because you have to pull this, specific ball, and then this specific ball, and you pull a bunch of specific balls. Now, a much more likely outcome is 42, and then once again 1. You only have to pull 2 specific balls, and that means the probability of this outcome of success is going to be much more than the first one. And we still don't know the probability. Like, okay, you could calculate this probability, each of these 2 probabilities, but you'll probably be able to notice there's no good systematic way to sort of add up all of your desired probabilities, Well, you're thinking, all right, so we can't just do the old model of take every total over desired. But what does work is instead of looking at the entire space of outcomes, we're going to throw away information. We're only going to look at certain outcomes. Right. Instead of measuring, everything, instead of encapsulating all the information in our probability, we're going to laser focus on a small portion. All right. Enough with this whole talk about, 64 balls, even number. All right. Let's just give a much easier problem. And I strongly encourage people to send their ideas in the chat. There already have been people sending their ideas in the chat, and there's many good ones. All right. So here's a similar problem. 64 balls. What is the probability the first odd ball drawn? 1. All right. So same problem as before, basically, except let's say you have 64 balls, 1 through 64. What is the probability that the first odd ball drawn is a 1? Yep. I've already been getting answers. I'll give a little bit more time for people to start throwing their ideas in, because I think this really distills the idea down to its substance. All right, so the answer is 1 over 32. And here's the idea. Once again, if we try to go back, sort of the parity I was displaying, where you look at all the total possibilities, you have 2, 4, all the even numbers, ... then drawing 1 is much less likely than just drawing 1, right? But nobody thinks this way. If we distill it down to this, it becomes really clear that the even numbers don't matter. What if we just consider our 32 oddballs and we've only the first odd ball drawn, right? And, for some reason, when we distill the pattern really clearly, what's the probability of first odd ball drawn is 1? It sort of instinctively eliminates the even balls for people. And this sort of puts the idea together. And the probability that the first odd ball drawn is 1 is 1 over 32, because each of the odd balls are symmetric in a way. Like, there's nothing separating them apart. And there you have your answer. Because the reason our different outcomes didn't have the same probability is because they were not symmetric. But now, when we're only looking at the first odd ball drawn and ignoring all the even balls drawn, that is when we sort of really get the idea. That is when we understand. That's when we're able to actually just simply compute the probability. Because we've thrown away information, we've thrown away the asymmetry, and now we are left with a symmetrical outcome. Because we're just looking at the probability the first odd ball drawn is 1. All right, so now, armed with this idea of throwing away information, let's look back at this problem. 64 balls labeled with the integers from 1 through 64. All right, so you can have a set of all the odd numbers. 1, 3, ... 63. But then they're asking this peculiar question about 42. And instead of thinking about the question, instead of thinking of oddballs and 42 being the same, what have we just said? This. The game ends. Balls are not removed anymore after 42 is drawn as well. Right? What if we just treat 42 as an odd number, basically? Well, nothing changes because there's no difference whether you draw 42 and continue to draw balls or whether you draw 42 and stop afterwards, because you've already won. You already drawn 42. It won't change whether 42 has been drawn by definition. So with this approach, we have 32 total numbers, or 33 total numbers. We have 32 even numbers and 1 odd number, and that totals up to 33. So if 33, and because there's nothing distinguishing these numbers from each other, we've established that. We've sort of thrown in a little shift of perspective as well here. There's nothing distinguishing these numbers from each other. So 1, 3, 63, 42. The probability is 1 over 33. So to recap, we have an asymmetrical structure. If you try to blindly analyze the outcomes, desirable outcomes over total outcomes, you're not going to succeed because there's asymmetry. Not each outcome has the same probability. So to that end, we throw away information. And by throwing away information and only laser focusing on one specific part, we restore the symmetry that we need to solve the problem. And with that symmetry back, we can actually solve it. All right. So now we want to actually take a look at our initial problem. Now this one is a lot harder because the idea of symmetry, of throwing away information to get back symmetry is so hard to notice. If we look at this problem, it is so easy to notice that the probability is 1 over 32 because all the odd balls, there's no difference between them. I don't pretend there's a difference between them. There's just no difference, right? it doesn't try to disguise itself. It's really transparent. Now this one is a little less transparent. You have to actually realize that 42 is basically an odd number. There's no difference between 42 and the odd numbered balls. But once you've done that, you realize, oh, there's symmetry, and you're done. Now this one is really balls. But most people are not really used to the idea of a unicorn or a thing that moves in this manner. And because of the novelty of the setup, it's really hard to discover this whole idea is symmetry. But, and I'm about to spoil this entire problem, here's the only thing you care about, the laser focus. What is the first time Andy steps in between the interval 1984 and 2019? All right. The only thing we care about is the first time Andy enters this interval. Now, why is this the case? Here's why. There's only one time he can enter this interval because the way it's defined, he moves forward. And the way the problem is defined, the probability of landing on each number, any number in this interval, is the same. So the only thing we care about is this move in the interval. And because of the way the problem is written, the probability you land on any specific number inside this interval is equal. Because if you're here, any number in front has the same probability. You know, somewhere below 1984, anything between 1984 and 2019 has the same probability. Therefore, there are 36 numbers between. And landing on any of these 36 numbers happens with the same probability. So landing in this interval for the first time. So the answer is 1/36. And the reason we have this laser focus on this interval is for two reasons. One, it only happens once, right? It only happens once. That is a really good candidate for something to laser focus on, throw away all the information you don't need. If you look at something that only happens once, then your probability of succeeding in answering the problem is a lot higher because it is much simpler. Now, two, it is the only way to get to 1984. You have to enter this interval to get to 1984. If you do not enter this interval, you do not, and if you don't enter this interval, you land on a number smaller than 1984. If you land on this interval, you land on a number greater than or equal to 1984. And once you're already inside the interval, you can't go back. So you can't get to 1984. And that is why we only look at the move that goes between 1 in 1983 and 1984 and 2019. Now, I'm going to give you guys a formal write-up to conclude this talk. So you guys really have something to look about. Well, it's not going to be like a full solution, but it's going to be an outline with all the key points distilled without any of the sort of philosophy. All right. Where did I get the problem? I wrote this one myself. I think I wrote this in 7th or 8th grade. 8th grade, I believe. I don't remember, but yeah. If you like this problem, I'll talk more about this at the end, but a group of myself and my friends have made a contest. So if you thought this problem was really clever, well, tomorrow, actually, there's going to be a contest. We have similarly clever problems. I think they're even better than this, because this one is just one I wrote on my own, but when working together with my friends, I sort of am able to write a lot better questions because we have more eyes on the board. I'll talk more about this near the end. Oh, what? Okay, something broke. That's all right. Let me clear the annotations because they're kind of getting out of the way. All right. So we use two states, and we look at the transition between them. That's the entire idea. If you really do a solution write-up, you can get the essence of it down into 2 sentences, like a complete solution in 2 sentences. In fact, I think this is what it is on my solution notes. It is literally 2 sentences. So thank you guys for coming to talk. I hope you guys enjoyed. If you're interested, in this topic, sort of, if you want my contact, I'm gonna leave it in the chat. If you want to see more problems like this, feel free to email me or just DM me in Zoom chat. I'll stick around. All right. Thank you everyone for coming. That concludes the talk.